Okay, so we just got done talking about how the photoelectric effect seems really weird. Okay, it went against the idea that light, it actually went against the idea that light was a wave. And I'll talk about the reason why. Maybe it wasn't clear from the last video, but what essentially happened was scientists' prediction was wrong. They thought that current in the photoelectric effect, you should have watched that video first, they thought the current would increase by turning up the brightness. However, it did, but it didn't make the electrons any more energetic, just released more electrons. In order to make the electrons more energetic, which would have agreed with the idea that light was a wave, the increased brightness should have made them more energetic, and that didn't happen. Only changing the frequency, or changing the wavelength, which means the frequency is changing, was ended up altering the energy of the electrons. And this was very strange, okay? Turning up the brightness did not necessarily make electrons start moving, and that was another thing. In fact, just turning up the brightness did not make a current flow. Current only flowed if the light had a large enough frequency. It was very curious. The brightness could increase the current once it started, but it couldn't create a current all by itself. And it didn't make the electrons any more energetic, which basically boils down to it didn't make them move any faster. Now, the reason that this did not fit with the theory that light was a wave is because every other wave that we have ever talked about, with every other wave, okay, so let me back up for a second. The point of this experiment is it showed it can't be a wave as we think about them because the energy of the wave was not proportional to the amplitude. Every other wave, this is true. In this case, it was not. And again, the amplitude for a light wave just means the brightness. Making it brighter did not make the electrons any more energetic. This was very strange to people. Okay, we were not sure what was going on. And it seemed like that was making, it was causing the idea that light was a wave to not be true. Which is really strange because we just got done talking about the double slit experiment, which showed light's a wave and not a particle. However, this makes it seem like light is behaving like a particle. You can imagine that light, a light particle comes in with a certain frequency, whatever that means. It comes in with a certain frequency. It's not carrying enough energy, doesn't release a photon. Light with a little bit higher of a frequency and more energy comes in, knocks an electron, loose. The electron shoots off with some speed. Light with even more energy comes in, a light particle comes in, even more energy, knocks a different electron loose. That electron has even more energy. This seemed to fit the idea that light was actually a particle and not a wave, which again is the exact reverse of the double slit experiment. Something very strange is going on here. It doesn't make a ton of sense if you look at it through a classical perspective. Okay? The normal theory of light as a wave didn't work here. Now it seemed that light was composed of particles that contained a certain amount of energy. That's the best explanation they could come up with. By the way, the photoelectric effect was actually done by Albert Einstein. He was the first to really explain it. Okay? And he helped to popularize this theory that they came up with. And this theory is called quantum theory. After they had these two experiments, we really had to redo our understanding of what light was. And so I'm going to summarize quantum theory for you very basically. Okay? First, electromagnetic energy. Okay, energy associated with electric and magnetic fields is emitted and absorbed in discrete amounts called quanta. Q-U-A-N-T-A. The singular is quantum, which is where quantum physics, quantum mechanics comes from, quantum particle. So all this means the discrete amount, when we talked about charge came in discrete amounts. You can't have a fraction of an electron. You can't have 1.3 electrons. You can't have 1.79 electrons. You have to have 1 electron, 2 electrons, 3 electrons, so on and so forth. charge is similar to this. Charge is discrete. It only comes in certain amounts. What this theory is saying is that the energy associated with light, with electromagnetic radiation, also comes in discrete amounts. It comes in certain amounts. They are called quanta. It comes in little bits. Okay? Each quantum, the energy of each quantum is proportional to the frequency of the radiation. Okay? So the light's frequency is proportional to the energy that it carries. And there is an equation for this. Let me pull up the reference table so you can see it. Let's see here. That's still going. Get rid of that. Regents, physics, reference table. Let's go to the reference tables. We're on to the modern section. Yes. Okay, there's the modern section. I'm going to zoom in. Okay, there's only 3 equations in the modern section. That first one is the one that is important right now. Okay, the energy, and I'll talk about this in a second, the energy is equal to H times F, or H times C over lambda. Okay, and if we go over, we see C is the speed of light in a vacuum, E is energy, F is frequency, H is Planck's constant, I'll talk about that in just a minute, and lambda is the wavelength. Okay? So, the equation for determining the energy is right in the reference tables, I believe page 5. It is E equals H times C, H times F, or HC over lambda. If you want to know where the HC over lambda thing comes, it comes because, if you remember this equation, V equals F lambda, if I'm talking about light, light moves at the speed of light. C equals F lambda. If I solve this for F, F is equal to C over lambda. That's all we've done here. We replaced F with C over lambda. Okay? So, this is weird. The energy is proportional to the frequency. And we have this weird constant H. H is known as Planck's constant. P-L-A-N-C-K'-S. Planck was a very famous physicist who was one of the first ones to theorize about things coming only in discrete amounts. The energy only coming in discrete amounts. This is also known as quantization. Okay? Planck's constant, if you look on the front of the reference tables, has a value. Let me scroll out again. Planck's constant has a value that is right here, 5th up from the bottom, of 6.63 times 10 to the negative 34th joules times seconds. 6.63 times 10 to the negative 34th joules seconds. Okay? Now, if you remember, you might have seen another word under the E in this equation. That word was photon. It's just another word for a quantum, a particle of light. Photons are particles of light. Okay? They are massless particles, yet they have both energy and momentum, which is really weird if you think about it. When you think about a particle carrying energy with it, you often think of kinetic energy, 1/2 mv squared. Mass is in the equation. Yet photons do not have mass, but they can carry energy. Momentum, the equation is P equals m times v, mass times velocity. Photons do not have mass, yet they can have momentum. And weirdly enough, they can also give their momentum and their energy to other particles that do have mass. And they can receive energy from those particles. Okay? They can transfer energy and momentum to other massive particles, and these interactions follow the normal conservation laws. You know, the idea is that momentum is conserved and energy is conserved that we talked about earlier in the year. So this is the general idea behind quantum theory. Okay? It explains more or less what light is. And the main takeaway is that light, it really isn't particles in the way we're used to thinking about them. It's also not waves in the way we're used to thinking of them. It's a third thing that has properties of both. There's nothing else in the world, in the universe, like light. Okay? It has characteristics of both that appear in different situations. And we have a name for this idea that light has both wave and particle properties, but it's something else entirely. And that idea is known as wave-particle duality. Wave-particle duality. So you might think that this is the end. We're like, okay, yeah, light, cool. It has properties of both. Great. But it actually gets weirder. Because we just said light has, what we always thought was a wave, has particle-like properties. And still has wave-like properties. But, of course, a particle, something like this, something like your tennis ball, yeah, that's just a particle. There's no waves about this whatsoever, okay? No wave stuff. But then later on, scientists did some experiments where they actually did the same double slit experiment that they did with light. And if you guys remind me in class, I will show you a double slit experiment. It's really kind of neat. They did the same double slit experiment, but instead they put electrons in here. It's kind of like the example I talked about with the tennis ball gun, where you're shooting tennis balls through these slits, and you would expect them only to line up like here and here. They did this with electrons. They said, let's put an electron gun here, shoot electrons through the slits, and see what happens back here. Because some people said, I bet something weird happens. And other people are like, no, nothing weird's going to happen. They're particles, they're going to go like that. And you know what happened? They shot electrons through these slits, and they got fringes of electrons. Not just behind the slits. They got electrons over here, they got electrons over here. They had different fringes just like light had done. And so someone came up with a good idea. Well, maybe the electrons are knocking into each other and just by chance producing that pattern. So they came up with a way to shoot one electron at a time. And what happened was, even when they shot one electron at a time, it took a while for the picture to build up. But the one electron at a time thing still made these patterns. The electrons weren't bumping into each other. Somehow the electrons, these particles that we thought we understood, were undergoing interference and diffraction. They were diffracting around this barrier, and they were interfering with one another, even when they shot one at a time. That is crazy. Okay? How can a particle diffract? Okay? Why would it bend just because it goes around a barrier? Why would it interfere with itself? People didn't understand this. Okay? And to be honest, we can explain it now, we can talk about it, we still don't understand why it happens. I mean, we know we can describe it, but we can't really say, why does it have to work like that, other than it just does. So, they did this with electrons. Then they said, let's try it with protons. They did it with protons. They did it with whole atoms. They did it with whole molecules. They even took viruses, things that are made up of possibly hundreds or thousands of molecules. I'm not up on how big a virus is. They're pretty small, but they're much bigger than just electrons. They took viruses. Researchers have taken viruses and shot viruses through slits, and the viruses interfere and diffract. These particles, these things that we can see and touch, not just waves that are kind of like,